you know, I could get a complex that my slides aren't in the book. And if I'd known they weren't in the book, I wouldn't have made them till last night. However, so it goes. I really don't need this, but so the first issue that one deals with in this is temperature. And let me contradict Joe a little bit. The oil patch has had wells that are reaching this temperature. You look at Shearwater, you look at Elgin, you look at the wells in the North Sea, and there are even some higher temperature ones in the Gulf of Mexico which are approaching those temperatures. But we're finding that with these wells, temperature remains a significant challenge because most of the tools that are designed particularly for directional drilling, MWD tools, and tools like that have a ceiling of about 275 to 350 degrees Fahrenheit. And you can see this pink shading goes to 275. You know, there are logging tools that go to 500. You know, Schlumberger has a density tool. Baker has some tools that go to that. But by and large, most logging tools will not reach that. And as Joe mentioned, one of the successes that we did have on this particular venture was running through tubing logging. Because what that basically is we were running drill pipe. You run the drill pipe in the hole, we can continue to circulate chilled fluid. So when you drill these wells, because of the temperature, your mud is always chilled. We had 3 chillers on location. And your mud is chilled, you can run drill pipe in, and you can be circulating as you're going in. You reach bottom, you continue to circulate. Then you pump down your logging tools. And there's an open-faced bit at the bottom. The logging tools go through the bit, they latch, and then there's about 15 minutes of panic while you make sure that you've got a signal, and you can watch the temperature going 300, 310, 320, and you're not ready to phone Joe yet and say that you've got $1 million bill for damaging a logging tool. But once you have established you got a signal, it's a wet disconnect. You can pull it up. You can pull it out of the hole, and then you can log on memory coming out of the hole. And seriously, this was fantastic. The logs were good quality, and it worked surprisingly well. But those are tools that we did inherited from the oil field. That Schlumberger, in fact, bought a company that did through-bit logging. There are other vendors that are out there, and so there are opportunities, but there are many, many challenges because of temperature. The second challenge, and it's not a challenge, it's sort of a query, is that if we look at the HFTS X series that have been done in the oil field, you get situations where you look at microseismic signals that are similar to the work that Ratterman and his colleagues have published on the right. And what that says to me is that in a situation in some of these oil field scenarios, we're seeing very linear, very very independent fracturing systems. You can see the linearity at the right. And what my colleagues try and tell me is that natural fractures don't matter. And so that's a significant question, and it remains a point of contention, because this is an outcrop at Forge. As Joe has pointed out, this is a rotational scenario, so there is outcropping that is nearby. And even with exfoliation and erosional effects, you can see that there's a substantial number of natural fractures. Natural fractures in this particular reservoir. And our downhole surveillance suggests that is the case. So the question becomes, do these natural fractures really matter? So you have to remember that it's a combination of stress and natural fractures that come into play here. In scenarios where there is a dominant maximum horizontal stress, then maybe there's less sensitivity and there's more there's more linearity of the features. Unfortunately, as in most cases, finding the magnitude of the maximum principal stress is unless it's vertical, is always a challenge. So the fractures remain an issue. So let's think about this as we go through some of these highlights and challenges that we've identified in this program. Right from square one, when we drilled 5832, we used this as a pilot well where we were actually competing to be the Forge site. And we set a packer at the bottom of the hole, and we did in situ stress measurements. Right from square one, even at 200 degrees C, that packer leaked, despite the fact that it should have met those criteria. okay? Fortunately, we were able to just pump down the annulus because the casing was stout enough to tolerate the pressure, so we were able to carry out our stress measurements. But right from square one, we were finding that that there were complications with the stress field data. We had some tremendous successes on this well, mind you, as we worked up hole when we did a restimulation program in 2019. We restimulated the bottom zone, we perforated and fracked an intermediate zone, and it was a very good day when you saw the curve on the left, where you could see there was actual classic breakdown, there was propagation. It was one of the first times that stimulation through perforation had been effective. What we did learn from the microseismicity on this was that it was going to be a challenge. That location of these events, because of a single shallow wellbore with geophones in it, we could detect the events easily, and that was our charter, was to detect. But location was much, much more challenging. As Joe has pointed out, even today it's challenging, although we're very lucky. So one can ask some of these questions, and we don't have time to go through them all, but I really want to reinforce that stress measurement remains important and remains a challenge, particularly when you're trying to understand the role of natural fractures. And one of the mistakes, what I'll call a mistake, is one of the simplifications we make too often, is we say, well, it's a granite. The stresses are constant, okay? The stress gradient is constant. Well, I really don't believe that's the case. If one starts to look at forecasts from acoustic logs, you can see there's a lot of variation of these stresses with depth, and all of those variations impact the growth of the natural fracture, of the hydraulic fractures and the interaction with the natural fractures. I have colleagues at Lawrence Livermore that started to call this stress roughness. And I think it's a really good term, that there is a variation in these stresses, and candidly in our simulations, just because some of our simulations are so numerically intensive, we have not taken that into account. So from a geoscience perspective, I could have been given this talk, I could have been giving the same message in 1980, but stress remains important and don't be talked out of it. And it's not necessarily homogeneous in these igneous settings. The second thing I've talked about, of course, is delineation of natural fractures. I think despite our experience with HFTS and some of the things that we've seen in the Eagle Ford and the Permian, that the natural fractures can still play a role in certain circumstances. Joe has already emphasized this. We've had a great deal of trouble on our early wells. I think we ran 10 bridge plugs and packers, and we had 9 failures. Okay, and so it is something that remains a significant issue, and we have a lot of R&D that's going on that's funded by Forge. For example, we're looking at metal packers. WellTech is one of the vendors. We're looking at other companies that have packers out there. DOE has funded development of what Schlumberger calls their copperhead, which is a frac plug that can tolerate these temperatures, and it's a plug so that you can pump it. It's unfortunate. We would have used it on this last job, but Schlumberger internally didn't know that they had the device in their price book, and so it goes. So part of our job is outreach, telling the vendors what products are available and what products they've developed internally. And I'm very serious about this. But anyways, a lot of improvement that's going on there. But we still have questions. The temperature and the development of the packers, although the packer development has improved. As Joe mentioned, we had a very strong relationship with a Norwegian company called Interwell. And Interwell ran bridge plugs, and Interwell, as a Norwegian company, they're very serious about being involved in green energy. And so they were very, very interested in spending internal R&D money in developing and qualifying these packers. And they worked extremely well. They went in and they came out. And Joe has had some bad experience with bridge plugs coming out of the hole, and that's why he's so negative about all of this. But I tell him, hey, it's out there, and we'll be able to use it. The other thing that doesn't come into play, and I don't have really that much time to talk about it, is that in some of our earlier testing, we would see progressive, during injection, we would see progressive increases in stresses with the amount of fluid that was put in. And that suggests something that we might think, hey, that's poroelasticity. But I just want to talk to people from a geomechanics point of view that poroelasticity is a concept that requires a porous formation. And so you have to rethink your thinking, is that this is poroelasticity, likely due to the fact that you're inflating natural fractures. So again, I'm on the natural fracture kick, that it may have a role in terms of controlling and or impeding propagation of fractures. But it's something that remains a geoscience interest. Before the last frac job, we were quite concerned about the difficulties in breaking down, okay? We had an 8,000 PSI wellhead limit on these wells, and we were worried about breaking down these wells. And after that was over, I'm less worried. I believe that you put enough pressure on these, even below 8,000 PSI, even if there are no natural fractures present, and you can break this down. However, oil field experience will tell us that you can find zones that you cannot break down. And I'm sure we'll find some in granite as we go through this. And so this remains a particular issue. Joe has talked about this, okay? There's room for refinement of geophysical technologies for monitoring fracture growth. In the next well that we're drilling, mind you, though, we will be running 3 fiber optic strings. And I prefer it was just one, I mean, because I have to design the wellhead and we have to get those 3 strings in the hole. But we have 2 R&D vendors. This is Rice University, who is working with Silixa, and this is University of Texas, who's working with Shell, who will install these 3 fiber optic strings. And so with additional work that we carry out with fracturing on the first well, we will be able to see the hits or the interactions very, very clearly, pending installation of those strings. Yeah, I think this is important. This is important, and I think Forge has done a particularly good job at this. We have a strong seismic team, and that team has developed traffic lights and protocols that have been very effective. And indeed, in our new funding for research, we're funding an adaptive traffic light system that takes advantage of the microseismicity that you've experienced on the fly, and it adapts to what's going on. And so pretty exciting, but absolutely essential for the geothermal business to be situated other than near towns like Milford. If you want to move this to pseudo-urban areas, microseismicity remains a huge, huge challenge. And these adaptive traffic light systems are extremely important. So we've drilled this well, and I won't go into it. Joe has already talked about the successes that we have with our bits. We learned a lot from mechanical specific energy, but it was more than that. It was simple things. At first, we did in fact try a PDC bit in our first well. We drilled the first well mostly with roller cone bits, because that's the heritage of geothermal, is roller cones, because traditionally they've been more reliable than PDC bits. But a lot has happened in the last 20 years with PDC bits in terms of ruggedizing them, improving the substrates and the tungsten carbide and the manufacturing. And so they hold up a lot better. But the reason that PDC bits will fail is because you don't put enough weight on bit. And that's one thing that we really learned from our colleagues at A&M, is that you have to weight these up as much as possible, and you actually have to run step tests where you're increasing the weight, you're increasing the weight, you're increasing the weight. And a separate test for increasing the RPMs, increasing the RPMs, increasing the RPMs. And you're looking for a situation where you avoid resonance in the drill string. And you get as much weight on the bit as possible and as many RPMs as possible, and your rates will go through the roof, as Joe has pointed out. Now, not everything is pretty though, okay? Your rates will go up, but one of the things that we really noticed from our post-UBI surveys, ultrasonic borehole imaging surveys, and each one of these is about 10 feet long, 8 3/4 inch bit, so 8 3/4 inch hole, is you can really see where you're sliding and you're rotating, or where vibrations were just killing you. Okay, and vibrations are what are going to kill you in terms of bit life and in terms of hole quality. And we know from the oil field why we have to worry about this. We have to worry about this for our casing, okay? Because we're going to be fracking these wells. We're going to be putting multiple stages in these wells. First of all, we got to be able to run the pipe into the hole and not hang up on a ledge. And secondly, we want to avoid pinch points that we have where there's poor cementing where the casing is lying on a ridge. And so on our upcoming work, we're going to be concentrating on removing some of this. I mean, we reamed a lot even before this, okay? But reaming in granite is not like reaming in shale, okay? You don't smooth it out. Those things, it's like I tell my students, it's like a criminal record, okay? It's with you forever. Okay. And I won't say it's criminal. I mean, this was an unintentional felony, but we learned something from it. And so, what are the improvements? We're going to increase the shank length on the bits because that will avoid the vibrational effects. And much to Joe's chagrin, we're going out for rotary steering on our upcoming drilling. And that's a tremendous challenge. I mean, we tried vertical rotary steering on this well. And the problem that we had with that was the pad contact with the formations, that we could not get enough. The pads were taking so much of the weight that we couldn't get the weight onto the bit. And so the penetration wasn't acceptable. And the rotary manufacturers did not want us putting weight on bit. They actually sent us a terse note saying, don't go above this level anymore. Weight on bit, rotary steerables, this is a problem to cure. And it's less of a problem maybe in the oil patch, although in some hard formations it could indeed be an issue. And this is why we think that maybe our developments in rotary steerable will be a transferable technology. Packers we've talked about, and I've gone on way too long about them. But, so we'll go back and we'll say that, hey, number 6 on our top 10 list is looking at the consequences of hole rugosity and maybe minimizing those with rotary steerable. And we're always looking for further improvements in our OP, and we can believe that we can get there. And we want to extrapolate these techniques to temperature environments. And actually, this is moving. This technology is going out to the oil patch. I talked to one of our drilling supervisors when we were doing the frac work, and he said he had seen our bits on wells in the Permian Basin. So the NOV has hit a home run, and they're translating this not only to geothermal but to the oil patch. I'm going backwards. Story of my life. Okay, well, we haven't heard too much about cementing, and we sort of hang our heads in shame. Cementing is really hard in these wells, right? Think about the environment you're dealing with. You're dealing with such high temperatures in these geothermal settings that how do you get around that? There are two things you do. First of all, you load up with silica to prevent strength retrogression and to minimize cracking. And the second thing you do is you load up with retarders, because the last thing you want is a flash set. And so we've had significant problems with cementing. We've had flash sets, and we've lost a fiber optic cable because of that. We've had a poor cement at the surface, even though we had significant circulation to the surface. And so cementing is something that should be on everybody's list. And we're more cognizant of cementing now than we ever have been. It's hard to fund research in cementing because it's kind of a one-off. You can do stuff in the laboratory, but you really have to test it in the field. Lost circulation, we're lucky at Forge, right? Lost circulation is a huge problem in the geothermal industry. But at Forge, we can drill these wells in granite, and there are essentially no losses. And that makes sense, right? Joe showed you that picture, that this is a conductive thermal environment. Even though we've got all those natural fractures, those fractures are probably healed and not taking fluid. So we have not had great difficulties with lost circulation. But that does not mean it's not a significant problem for the geothermal industry elsewhere and must get a lot of consideration. There are other drilling methods that have relevance and could be considered. Air hammers, mud hammers. Although we have colleagues at EVOR. EVOR is a Canadian company that's looking at single well closed loop systems, and EVOR was spending a lot of money for mud hammers, but they looked at the success that we had with PDC bits, and they said, don't bother. We're going to just use PDC bits. And so if mud hammer technology can be improved, and it has to be mud hammer technology, doesn't have to. I mean, air hammer is fine. Then there is relevance there. And everything, and fiber optics. I mean, we've had operational difficulties. I'm running way over time, so I need to skip some of these, even though they are the slides that interest me the most, because they're about the hydraulic fracturing that went on. And so I'll go through them very quickly, even more quickly than I have been in the past. So Joe talked about 3 stages that were pumped. The first stage was a slick water stage in an open hole section. So I need an app to help me with that, is what Siri told me. And it's very true. 3 stages pumped, monitoring wells. The first stage, 50 barrels a minute, we stepped up. And you can see the pressure on this. This is surface pressure. It's shown in red. And in the lime green, it's showing the rate. And the reason that we stepped up in the rate is we didn't quite know what was going to happen, okay? And we walked it up to 50 barrels a minute because frankly, you need these rates. And you say, well, 50 barrels a minute, even that's a lot less than what we pump in the oil patch. Well, and that's probably true in this open hole section because it was 200 feet long. But the rates that we got to in the other sections were probably actually higher than what you would have in an equivalent section in the oil patch because we only had 1 cluster. We only had 1 cluster intentionally in those other zones so that we could maximize the fracture that we created, and there wouldn't be competition for fluid between clusters, and we would sort of guarantee that we would have a fracture that was adequately long enough to intersect in the future. So a very classic situation in this. The pressure was going up. We had an 8,000 psi surface limitation. No issues whatsoever going to those high rates in this. And we did step up and step down, and we did those so that we could back out the friction on the way up and on the way down, and actually compare the friction on the way up with on the way down after you had actually pumped the jobs. The second stage, as Joe mentioned, we sealed with these interwell bridge plugs. Very, very successful. And of course, the only drawback was, as Joe mentioned, we could not set these on wireline, and so that meant he and Shirley had to scramble to get a rig at the last minute. And our friends at Frontier, I'm going to put in a plug for Frontier Drilling. They really saved our bacon because you have a frac job scheduled. If you postpone a frac job, you're looking at 3 months if you're lucky. And so they brought this rig back to life. It had been laid down for 2 years. I call it Lazarus 1 because so many components had been stolen for other rigs, and used elsewhere. But it really was a fantastic rig, and those guys were just outstanding. That plug aside, the second stage, cased, perforated, 20-foot gun. We were originally going to run a 10-foot gun. But, a wave of cowardice overtook us at the last minute, and we said, we'll run a longer gun to make sure that we hit any of these natural fractures that our colleagues had pointed out were there. What did we do? 6 shots per foot, 30-gram charts, 60-degree phasing. Standard oil field type operations. And as you can see, this walked right up, the pressure. This isn't a breakdown. This is actually a shut-in, okay, an intentional shut-in. And the reason that we did that shut-in is we had a company called Momentum AI monitoring the pressure for high frequency. And their best results came with a shut-in from 5 barrels a minute down to nothing at the end of the job. And so we wanted to duplicate what happened with a shut-in early on in the job and see if we could compare it with what happened later on in the job after you'd pumped all this fluid into the formation. And then one of our advisors is a fellow by the name of Carl Montgomery, and Carl is sort of a really recognized fracturing guru. And he suggested that we do a shut-in mid-job and see if there was any change in the microseismicity. We did not see any change in the microseismic profile with an aggressive rate change. So we, hard shut-in and hard back up to 35 barrels a minute. 35 barrels a minute, we went to a lower rate because of perforation friction, okay? And it looks like we could have got a little higher. We probably could have got to 50 barrels a minute because we could have pumped to 8,000. And you can see this is a classic, there's no proppant, classic fluid behavior suggesting upwards fracture growth because the pressure is decaying. So, really beautiful, beautiful signature on this frac job. And then stage 3, another bridge plug, 35 barrels a minute. It was similar, except in this particular case, we ran carboxymethyl hydroxypropyl guar. So that's a fluid. That hydroxypropyl guar is guar is a bean grown in India, South Texas, wherever it's ground up, processed to become hydroxypropyl, and you add water to it, and you get a viscosified fluid at a temperature that we normally deal with in hydraulic fracturing operations. You add zirconate to that or borate to that, and you cross-link that fluid, and you get a higher viscosity. But not at 450 degrees Fahrenheit static temperature, okay? We probably had 20 centipoise is what we figured. But that's better than half a centipoise with water. The water had friction reducer added to it, but the friction reducer was likely gone by the time it hit the perforations. And so we probably have, we have some carrying capacity. We also tried running micropropant. There are a couple of vendors of micropropant that are out there now. It's probably not a fair test because we ran relatively small concentrations. The reason that we wanted to run it was to see that when we drilled the second well, if we could intersect a man-made product. Because in some of the, as I understand in some of the HFTS work, and this was advice given to me by Steve Cobb with Premier, they had difficulty picking out formation from frac sand. Now, we probably won't run frac sand anyways because it can't tolerate the temperature, but at least we have something man-made in addition to the tracers that Joe talked about. So beautiful, beautiful, beautiful radial, pseudo-radial fracture growth, or at least upwards elliptical. This is an older figure than the one that Joe has showing the seismicity, but really, really a classic fracture signature and, a tremendously successful job with hot fluids coming back to the surface. And tracers, somebody was asking about tracers. Maybe it was you, Evan. The tracers, we didn't see them in any of the offsets, but the offsets are far away. What we are anticipating is that these tracers can survive at those temperatures for extended period of time. And so we'll look to see if we encounter the tracers when we drill the second well to intersect. So when we drill the second well, we'll be looking for tracers. We'll be looking for lost zones that represent fractures that are growing. And we will also be circulating through the first well. So Al's looking at his watch, and so I'm done. Okay, so here are all the questions. Here are my top 10 questions for EGS, and it goes down to this one that says it all, and we don't know yet. As we discussed, once we start circulating, we're going to really start to understand. What are we going to understand? We're going to understand the potential parasitic losses and the overall economics of long-term circulation. We're going to understand the thermal depletion that occurs and whether this is a reservoir that has the longevity that we're going to talk about. And we're going to see how much conformance really impacts our performance. So, sorry, but it's like all of us. I mean, we just get carried away. Okay, thanks very much.